All right, welcome. Look, if you're an engineer, your whole job, really, is to understand and predict how systems change over time. And first-order, ordinary differential equations, well, they're one of the most fundamental tools in your toolbox for doing exactly that. So let's dive right in and see how we can use math to describe the world around us.
So here's our game plan. We're going to start with the big picture, the why behind modeling. Then we'll get into the nitty-gritty and define our main tool, the ODE. After that, we'll figure out the difference between a general solution and a very specific one, walk through a real-world example together step by step, and finally, and this is key, we'll learn how to actually interpret what our answers mean.
Okay, so before we start crunching numbers, let's talk philosophy for a minute. What are we actually doing when we create a mathematical model? What's the point of it all?
This right here, this diagram is everything. It's the entire engineering process in a nutshell. We start with some real physical system, an electrical circuit, a population of bacteria, whatever it is. We then translate how that system behaves into the language of math. That's our model. We solve the math, but we don't stop there. The most important step is taking that answer and translating it back to see if it makes sense in the real world. It's this beautiful cycle, from reality to math and back to reality again. Now that we get the why, let's get to the what. It's time to meet the star of our show, the ordinary differential equation, or, as we all call it, the ODE. This is the language we use to describe pretty much any system that involves a rate of change.
So what is an ODE? Well, at its core, it's just an equation that has derivatives in it. That's it. And the order of the equation, that just tells you what the highest derivative is. So if you see a y prime, like in that first example, it's a first-order ODE. See a y double prime? Now it's second order. You get the idea. For our purposes today, we are focusing entirely on these first-order equations. And trust me, they are incredibly powerful. Now, you're going to see ODEs written in a couple of ways. There's the implicit form, where everything's kind of jumbled together, but with a little bit of algebra, we can clean it up and get it into this much nicer explicit form, where the y prime is all by itself on one side. That is our standard form. That's the one we always want to aim for. Okay, this right here is a huge mental shift. When you solve an ODE, you are not looking for a number, like 5 or -2, you're looking for an entire function. Just check out this proof. We're guessing that the function h of x equals c over x is a solution. So we take its derivative, we plug it back into the original ODE, and boom, the left side equals the right side. It works. It satisfies the equation perfectly. That means our function is a valid solution. So that brings up a really important question. If we found a function that works, is it the only one? I mean, what about that c in the last example? It just seems like it could be anything, right? Let's dig into that. That random constant c is actually the key to what we call the general solution. And this graph shows it perfectly. It's not one single answer. It's a whole family of an infinite number of possible answers. Every single one of those gray curves satisfies the equation. Changing c just slides the curve around, but they're all technically correct solutions. So how in the world do we pick the one curve that actually describes our real-world system? Well, we need more information. We need a starting point, an anchor. And that is exactly what an initial condition is. It's a known value at a known point in time. For example, maybe you know the voltage on a capacitor the moment you flip the switch. As soon as you have that piece of information, you now have what's called an initial value problem, and you can nail down the one single unique solution you're after.
Let's make this super concrete. Let's say we have our general solution, y equals c times e to the 3x. And we're given an initial condition. When x is 0, y is 5.7. Okay. All we have to do is plug those numbers in, and since e to the power of 0 is just 1, the math is dead simple. C has to be 5.7. And just like that, we've gone from an infinite family of solutions to our one and only particular solution.
All right, the theory is great, but let's actually get our hands dirty now. We're going to put all these pieces together and model a real-world problem, radioactive decay, from start to finish, from the physics to the math to the final answer. We're going to follow a simple, repeatable, 3-step playbook. Step 1, setup. We translate the physics into an ODE. Step 2, solve. We do the math and find the particular solution. And step 3, interpret. We figure out what that mathematical answer actually means in the real world. Setup, solve, interpret. Let's do it.
Step 1, setup. Let's break down this sentence and turn it into math.
rate of change, okay, that's just dy by dt, is proportional to the amount present, well, that becomes k times y. Now, the key word is decay or decomposing. It's decreasing, which means we have to stick a negative sign in there. And finally, we're told we start with a half a gram, so that's our initial condition, y of 0 equals 0.5. See? Direct translation. Step 2, solve it. Now, we happen to know the general solution for this type of decay is y equals c times e to the minus kt. So, just like we did before, we plug in our initial condition. 0.5 equals c times e to the power of 0. And since e to the 0 is just 1, that term basically vanishes, telling us straight up that our constant c has to be 0.5. Our particular solution is y of t equals 0.5 times e to the minus kt. Done.
We've got our function. It looks great. But we are not done. An equation isn't the end goal. What does this function actually tell us about what's happening to a radioactive substance? This is the interpretation step, the so what. And when we plot our solution, this graph tells the whole story visually. The curve starts right at our initial amount, half a gram, and then it decays exponentially over time. Now notice how it gets closer and closer and closer to 0. But it never actually touches the axis. This is called an asymptotic approach. It tells us that, mathematically speaking, the substance never completely vanishes. It just gets infinitely small.
So let's do a super quick recap. An ODE is an equation with a function and its derivatives. The order is just its highest derivative. A general solution is that whole family of curves with a constant c. The particular solution is the one unique curve we find when we use an initial condition. And modeling is that whole beautiful process of going from the physical world to a mathematical prediction.
We just walked through radioactive decay. But here's the truly amazing part. The exact same mathematical process, that simple first-order ODE, also perfectly describes the voltage in an RC circuit, the growth of a bacteria culture, or a simple chemical reaction. The physics might be different, but the language of math is universal. So the only question I have left for you is, what physical system are you going to model first?
All right, welcome everyone. As an engineering professor, I know that our core job really is to understand and predict how systems change. And today, we're going to add a fundamental tool to your professional toolkit for doing just that. We're diving into the world of first-order ordinary differential equations, which is really the bedrock for modeling dynamic systems. So let's start with the big picture, right? Why do we as engineers actually need to master differential equations? What is the fundamental connection between all this math and the real-world systems that we design and we analyze every single day?
You know, this quote right here, it really hits the nail on the head. The universe isn't static. It is constantly in flux. From the motion of planets to the flow of current in a wire, change is really the only constant. And it just so happens that differential equations are the precise mathematical language we've developed to describe, model, and even predict that change.
Just think about it for a second. An electrical engineer models the transient response of a filter. A mechanical engineer is analyzing vibrations in a bridge. A chemical engineer is tracking reaction rates. Every single one of those is a system in motion. And here's the kicker. ODEs are the only tool that can handle systems where the rate of change is also changing. So we absolutely need a framework to model, predict, and, ultimately control these dynamic systems. And that's exactly what we're here to build today.
Okay, let's get our hands dirty and really forge the first tool in our kit by defining exactly what it is we're working with. Before we can solve anything, we've got to speak the language and understand the components of our model. Now, what's so interesting about this is that it gives us our master blueprint, our core methodology for tackling pretty much any physical problem. It's a three-step process. First, we translate the physical system into a mathematical model. That's our differential equation. Second, we solve that equation. And third, and this is absolutely crucial, we interpret that solution back in the context of the real world. This loop right here is the very heart of engineering analysis.
Okay, so here's the textbook definition, an ordinary differential equation, or ODE. The keywords to lock onto here are derivatives and single independent variable. But what does that really mean? In simple terms, it's an equation that describes a rate of change with respect to just one variable, like time or maybe distance. If you see a y prime or a dy dt, you are in the world of ODEs.
Right? But not all ODEs are the same. We classify them by their order, which is really just a fancy way of saying we look for the highest derivative involved. A second derivative, that's a second-order ODE. For now, though, we're starting with the simplest, most fundamental, and honestly the most common type you're going to run into, first-order ODEs. These only involve the first derivative, things like velocity or a rate of decay.
Think about it. A tool is kind of useless if you can't set it up for a specific job, right? An ODE can describe a whole category of physical behaviors, but we're usually just interested in one specific scenario. So let's see how we go from a general formula to a specific, actionable answer.
So the first time you crack an ODE, what you get is something called a general solution. The key feature here is this arbitrary constant C. I like to think of the general solution like a circuit schematic. It shows you all the components and how they're related, but the specific voltage or current values, they aren't locked in yet. It represents a whole family of possibilities.
And this is a perfect example. For the solution y equals c over x, that c could be 1, it could be -5, it could be pi. Each value you pick for that constant gives you a totally different potential outcome, a unique curve on the graph. And every single one of those curves perfectly follows the rule of the original equation. So this brings up a really critical question for us as engineers. With literally infinite possible solutions in our family of curves, how do we pinpoint the one single unique solution that actually describes our specific physical problem? How do we find the one that really matters?
And the answer, thankfully, has a name, the initial value problem, or IVP. We give it a known starting point, like a snapshot in time. We say, okay, I don't just know the rule of how this system changes, I also know that at this exact point in time, x0, the system had this exact value, y0. That single data point. That's the whole key.
Okay, so here's the bottom line. The initial condition lets us solve for that arbitrary constant c, and we can lock in the one single particular solution we actually care about. It's just like taking a voltage measurement at time 0 in a real circuit. That one measurement lets you predict the entire future response. We go from a whole family of possibilities to a single concrete reality.
Okay, enough theory. Let's make this real. We can see how all these pieces build a complete picture by walking through a classic, really fundamental example from our text, radioactive decay.
So we're going to stick to that four-step blueprint we talked about. We'll model, we'll find the general solution, then the particular solution, and finally we'll interpret the result. Let's get started with the model.
First up, the model. Okay, so what do we see in the real world? Well, experiments show us that the rate at which a radioactive substance decays is directly proportional to how much of the substance you currently have. Makes sense, right? More stuff means it decays faster. We can translate this into the language of math. The rate of change of y with respect to time, that's dy dt, is proportional to y. And the minus sign is there because the amount is decreasing. And boom, just like that, we've built our first-order ODE.
All right, steps 2 and 3. Let's solve this thing. As the text shows, if you integrate this ODE, you get the general solution. Y of t equals some constant c times e to the minus kt. This describes that classic exponential decay family of curves. Now we calibrate it. We apply our initial condition. We say we know that at time 0 we started with 0.5 grams of the substance. We plug that in, and right away we find that our arbitrary constant c has to be 0.5. And just like that, we have our particular solution, locking in the exact behavior of our system.
And finally, the last step, we interpret what this all means. This graph, this is the direct output of our particular solution. It's just a plot of y of t equals 0.5 times e to the minus kt. And what does it show us? Well, it visually confirms exactly what we'd expect to see in the real physical system, a quantity that starts at 0.5 and just decays exponentially over time. The math has perfectly captured the physics. It's beautiful. Okay, so let's zoom out. After all that, what's the big takeaway? What have you really added to your professional skill set today?
It's this. You now have this powerful, repeatable process, that loop of modeling, solving, and interpreting, and it is a cornerstone of advanced engineering. And believe me, this is not just some textbook exercise. This is a fundamental tool that you are going to use to analyze and design complex systems for your entire career.
So I want to leave you with a final thought experiment. Let's bring it back to electrical engineering. Picture a simple RC circuit, just a resistor and a capacitor. We know its behavior follows a first-order ODE. So what physical property of that circuit, what measurable quantity, would you need to know at time 0 to find its one particular solution? Really think about that. That's where the math meets the reality on your breadboard.